All right, guys, we're going to go ahead and take a look at mean value theorem. All right, now there are three value theorems that we use. I think we've already done one, the intermediate value theorem, and there's the extreme value theorem, which we learned earlier, which I told you guys is kind of like pointless. It just says if it's on a closed interval, it has to have a high point, it has to have a low point. And then the mean value theorem, okay? Mean value theorem is the most common one. You're going to use intermediate value theorem is the second most common, and we don't value theorem all that. All right, so let's discover the mean value. So first of all, draw the secant line between the points A, F of A, and B, F of A. Okay, so here we go. That's a secant line. Okay, then we want to draw a tangent line that is parallel. So, okay, so the idea is like draw a parallel line. All right, I don't want to make it that close. Hold on. All right, there we go. There's a parallel line. And a tangent line means somewhere on the curve where it's exactly that same, it has that same slope. Here is a point where the tangent line has the exact same slope as the secant line. Okay? All right, so let's do one over here. So here's my secant line. Okay? And then if I'm trying to find a tangent line that is basically, exactly parallel to that, well, there's one right there, right? And then there's another one right. There we go. That looks parallel. Right here. All right. This one happens to have 2 points where the tangent line is parallel to the secant line. All right. Now let's look at this next one. Okay, there we go. I've got a line parallel, and I want to find the point where it goes. Well, none of those points along there, none of those points along there. And that point doesn't work, guys. That's a cusp, right? So this one actually doesn't have one. Okay, so right next to this one, we're going to say it's not possible. And why is it not possible to draw, there's all these, possible tangent lines coming in here. None of them are ever going to be parallel. Line down here. Well, the reason why is because it has cusp, so we can't do it. Okay? All right, perfect. Let's look at number 14. Here we go. Here's my secant line. And hopefully you guys can tell pretty quickly that line is not going to go anywhere on here. There's no parallel anywhere on here. Okay? So that doesn't work. And why is that? Well, it's probably because we have this asymptote right down the middle. Okay? So this one is also not possible. And the reason is because it is not continuous. Okay? There's an asymptote there. So it's not continuous. So we can't find anything that would work. All right, this one, dude, I can't even draw a secant line. Not possible. And the reason for that would be, well, this keeps on going forever, however you want to say that, right? But the way I think of it is that there's no end point for me to draw a secant line on. Okay. And then here's my last one. All right, here's my line. And then you guys can see that there's a little issue with this one here because, it should be there, but that's not a point. Okay. Well, again, it's not possible in this scenario. Okay. Because there is a hole, or we can say it's not continuous. All right. Okay. So what does this say? Well, these are like examples. We kind of talked about each one of these. All right. Um, okay. So now we're looking at, I guess we're discovering it again. All right. Draw a secant line between the points 2f of 2 and 5f of 5. Okay. Okay. Draw all tangent lines parallel between 5. So I feel like the only one was like about right there, maybe. Does that look right? Right there. The value of c, where c f of c. All that's like really saying is like, what number is that? It looks like a house. And 3 is a number between 5 where I can draw that tangent line and have it be parallel to the secant line. Okay. All right. Let's look at this one. There we go. And between 2 and 5, I feel like there's actually a couple. There's one right there and about right there. Okay. So this one is at, I don't know, maybe 2.5 or just close. And this one is at maybe like 4.5. Okay. That's the interval. Interval on these problems is 2 to 5, and those are all right. And then here, oh dang, this one's got 3, right? Got 1 here. What does that look like? Maybe like 0.5, 3.5. I don't know, 4.5. I'm like just totally estimating here. Okay. And those are the C values where the derivative of tangent line or the slope of the tangent line is parallel to. All right. This is what the mean value theorem says. Okay. Now, first of all, in order to even use the mean value, we talked a lot about should have to meet certain. And we discovered what the conditions were on these problems right here, right? Why was it not possible? Because there was a cusp there. Why was this one not possible? Because there was an asymptote. Why was the other one not possible? Because it didn't have an end point. This one was not continuous. It had a hole. Okay? So let's read. The conditions say f has to be continuous on the closed interval a to b. Means it has to have endpoints, right? Like that one graph we saw, it didn't have an endpoint. And it has to be differentiable on a to b. What does that mean, differentiable? Ever between a and b. Now, we don't take derivatives at endpoints. Uh, this has on it, okay? Because endpoints, we don't really talk about differential endpoints. But everywhere in between, it basically means no cross, no sharp corners. Okay, this one continuous means no vertical asymptotes, no holes, no jumps. Okay, these examples up here are all examples between 2 and 5 where they are continuous and differentiable. Okay, this one is not differentiable at that point, but that doesn't matter because that was like my end. All right. Everywhere between 2 and 5. Okay. Then, blah, blah, blah. Okay, there's a number E somewhere in the interval. We could find a number, at least one number. There couldn't be more, where f prime of C equals f of B minus f of A over B minus A. Okay, so you should be thinking right now, what on earth does that mean? This represents the tangent line, the slope of the tangent line, or the instantaneous rate of change. Guys, that is the derivative, okay? This one represents the slope. F of B minus FA over B minus A, you should recognize that as a slope formula. That's the slope. There's a spot where the derivative has to equal the slope. And when we solve that equation, we solve for C. Okay? So let's read this. Informally, the mean value theorem states that given the right conditions, continuity, differentiability, there will be at least one tangent line parallel to the secant line when we were drawing this. In other words, the instantaneous rate of change, slope of the tangent line, will equal the average rate of change, the slope of the secant line. Okay? So let's do some problems where you will have to, wow, problem, start on you. Do not worry. All right, so here we go. So what we do is we take my equation, which is right here, and we take the derivative, okay? Now, before we start, actually, before I even do that, I have to meet my condition, okay? Meeting your conditions basically goes F is continuous on 3 to 6. That is true, all right? Because look, this is not continuous at 0, okay? But 0 is not in my interval, so it's continuous on 3 to 6. And then let's go ahead and take the derivative of this. Well, it's away. Now look, guys, we know this is negative 6x to negative. So the derivative is negative, nope, positive, when positive 6x squared, 6 over x squared. And guess what? That derivative exists everywhere. So it's differentiable on 3 to 6. Okay, so we check, we meet our conditions. That's the derivative. Then we find the slope. Now, for the slope, you take your endpoints, 6 and 3, and you go f of 6 minus f of 3 over 6 minus 3. Okay, f of 6 means that I got to go back in here and plug in 6 into my original problem. If I plug in 6, I get 3 minus 1, which is 2. And then I have to go back and plug 3 to my original problem. 6 divided by 3 is 2. 3 minus 2 is 1. So I get 1 over 3. That's my slope. Okay, guys, derivative. Okay. Okay, guys, then all we do is we go derivative equals slope, and we solve it. Okay? Now, I swear, I have classes all the time. They can do the calculus and then mess up on the algebra, right? You guys know that. Okay? Gotta remember back. Y'all remember cross multiplying? All right, cross multiplying says if I go this way and I multiply like x squared times 1, I get, if I go this way, 6 times 3 is 18. I square root both sides. X is plus or minus the square root of 18. Now listen, I don't care if you guys simplify that down or not. Listen, if it's an FRQ, we would leave it like that. If it's a multiple choice question, okay, it's like, that would break that down for us. So it actually would be plus or minus 3 root 2. Okay, now here's the thing, guys. We have to figure out which of those is in my interval, or if they both are. Well, if I'm between 3 and 6, the only one that's going to be positive. Oh, and we're not supposed to use x, we're supposed to use, okay, so we're going to pick the positive. All right, that's it. Derivative equals slope, okay? Now, I'm going to start you guys' homework with you here because this can be like a little bit. All right, so last night y'all did, oh, hopefully that. And then night 23:3. Okay, the first thing you got to do on these sections, this section right here, and we're going to do this too, does um the condition. Half of these do and half of them don't. Okay, so we're going to go through, we'll talk about every single one of them. And then we'll talk about, does it meet the conditions? And then for the ones that it does, we'll go ahead and do the problem. Okay? All right, check it out. Think about number 23. let's just think about the graph of absolute value of x. Now, I know you guys all know what this looks like for a absolute value of x. Boom. Okay. And this was on -1 to, all right. So look at it from -1 to 3. Is it continuous? Yes. Is it differentiable everywhere? No, it's not differentiable right there because of sharp corner. Okay. Oh, can I do the mean value theorem on them? No. And it says if not, explain why not. I'm just going to go ahead and say sharp corner at 0, which is in my, okay? Okay, perfect. All right, number 24. So we're not going to be able to do one. So we're not going to go back and do it. All right, number 24. You guys know what this looks like? Hopefully you should. This is just a parabola. Okay, now you are allowed to know for all polynomials that they are continuous and differential. Like you're just allowed to know that on anything that's like a polynomial. So this one, we are definitely going to be able to go back it. We're going to go. Okay, let's keep going. 25, is it continuous and differentiable? It is. Yep. So polynomial. Okay, 26. Now it's really good to know what the graph of x is 2/3 looks like. You guys know that so there's absolute value of x. The reason I like this graph is it's one of the few graphs that actually has like a naturally occurring cusp that's not like from a piecewise function or whatever. So there's a cusp. Okay. So from -2 to 2, are we allowed to do this? No. And the reason why is because it has a cusp at 0. Okay. So we are not going to. Now, how about x to the 2/3 on the interval from 0 to 1? Okay, well, let's go ahead and I could like this 0 plus x to 1. What do you guys think? Is it continuous? Yes. Is it differentiable? Yes. It wasn't differentiable at 0, but 0 is now an endpoint, and it doesn't have to be differentiable there. So because we're going from 0 to 1, I can do this. I can say it is continuous. And this one I would probably, I'm going to say it's continuous on 0 to 1, and it's differentiable on. And so we will be able to go that one. Okay. All right, let's look at number 28. Let's think about the continuity of this. Is this continuous everywhere? Well, what do you guys know about a rational function, whereas x minus 4 on the bottom? This has an asymptote at x equals 4. And because 4 is in my interval, we're not going to be able to do this. So it has a vertical asymptote at x equals 4. So whereas like number 23 and number 26 were both continuous but not differentiable, this one's not even continuous. All right, I can't even say it's like continuous there. So we are not going to do that. All right. What about number 29? Something is going on when x is 0. All right, you guys know what's going on right there. If I factored out x cut out, right? But it still has something when x is 0. This actually has a hole at 0. Because remember when we can, that means it's there. So we're not going to be able to do it because there is a hole at 0, which is in my interval, which makes this not. Oh. All right. Number 30 is okay, continuous everywhere, differentiable everywhere. Sine, this is a good one. The graph of sine is different. There's the graph of sine. It's always continuous and it's always differentiable. All right. And especially if we're just going from like 0 to 1, right? Or 0 to continuous, right? Okay. So this one is continuous everywhere and differential everywhere. And then 32, let's see if you remember what the graph of tangent looks like. Go ahead and take a look at it. Okay, this graph, I don't know if you guys remember, put the x-axis in terms of pi over 2. This graph has asymptotes at every pi over 2. So I was trying to go on this one from 0 to pi. This is not going to work. Okay. So, no, this does not because there is vertical asymptote at pi over 2, which is between 0 and pi. No, like there's only 5 questions that actually, okay? And then what you're going to do is you're going to do the mean value theorem on those 5 questions. All right. I will do a couple of them with you guys. Okay. So you're 24, 25, 25 to, 27, we'll probably do that one together also. Because it's x to the 2/3, so we gotta. Okay. And then we're gonna do 30. You guys can do that one on your own. And then 31, we will do that one together. That's on the interval 0 to pi. Okay, but I'm going to do these 3 with you, but don't forget to also. Okay, so let's start with number 20. All right, the derivative is x, and then we do the slope, right? Now, from -1 to 3, I go f of 3 minus f of -1 over 3 minus -1. Okay, f of 3 just means that I plug here, like 9 minus 9, 2. So that's, and then f of -1, if I put it 1 plus 2. Okay, so that's -4 over 4, which is -1. All right, so check it out, guys. We've got a slope. When we set them equal to each other, solve, add the 5, divide by 2, x equals 1. Or if you remember correctly, we're supposed to call it c. But there you go. And is that in my interval? And it is between -1 and 3. Okay, so all you're doing is derivative. Oh, all right. 27. So that's 2/3 x to the -1/3. And then we got to do the slope. Okay, so it's going to be f of f 0, 1, 0. When I plug 1 into here, 1 to the 2/3, 1. And when I plug 0 into 0. Okay, so this is my slope. Set them equal. Now, when I actually go to solve this, okay, I would bring the x to the 1/3 on the bottom probably, and cross multiply. All right, remember that can be cross multiply this. Okay, so I get 3x to the 1/3 is 2. Cross multiply. X to the 1/3 is 2/3. And then the way that we solve that is to get rid of a 1/3, we actually go third power. I'm going to remember to put. Okay, so 2/3 is 8, and 8 over 27 0 and 1. All right, let's do a trig example here. Okay, derivative of sine is cosine. And then my slope, I've got to go f of pi minus f of 0 over pi minus 0. Okay, f of pi, if I plug that in, sine of pi, that's over here, right? That's the point -0. Sine is the y-coordinate, so sine of pi is 0. And then 0 is over here. That's also 0. So 0 divided by pi is 0. Okay, so there's my derivative. I'm going to set these equal. Okay. Now, there's lots of places where cosine equals 0. Cosine equals 0 up at the top right here, because it's the front. Down at the bottom right here, 0 negative 1. And actually, if you keep going around an infinite number of times is where cosine equals 0. But we're looking for only on between 0 and pi. Where does cosine equal 0? At pi over 2. Okay. All right. So that's how you do those. So don't forget to go back to do we're in. Now, I also want you guys to do and it says that you can use a calculator on this. So I am going to actually bring up my calculator here. Oh no, there's a problem. All right, let's get this opened up here. And bring this over here a little bit. Okay. All right. So let's go ahead and just do this first one here. Okay, I want to put x to the third. Taking the time to do this because I want you guys with me. Just watch this. Don't fast. I'm watching. All right. Actually type it in because you're going to need help with how to do this stuff. Okay? On the interval -1 to 2. Now I think the reason that it's saying that you can use a calculator, because taking the derivative is pretty, I mean, it's 3x squared minus, okay? But I'll also show you how to do that part on the calculator, okay? But the big thing is actually figuring out what the slope is. It's letting me use a calculator. All right, check it out. Now that that's in my y, go like this. Alpha y equals fraction. And then you want to go to alpha trace y1 of 2. It's kind of like saying like f of 2 minus, and then go alpha trace y1 of -1 over 2 minus -1. Okay? And so it's just like a really fast way to get both. All right. Why else did it tell us that we could do this on a calculator? Well, okay, I need derivative of the 3x squared minus 4x and set it equal to 1. Well, the way that you do that is you put 1 on the calculator. Now, I actually don't want my original equation in there anymore, but I don't want to clear it. I'm just going to turn it off by hitting enter. And I'm going to graph this. Okay, there's my derivative. There's my slope. So where is it? Well, you guys can see it. It's like right there and right there, right? Between -1 and 2, it actually looks like there's going to be 2 answers. Okay. Here we go. Intersect and then you just move it over and you just hit enter 3 times. 1, 2, 3. So my intercept is negative 0.215. Okay. And then again, I go calculate, intersect, I arrow over, and I hit it 3 times. 1.5. Okay. So, both of those are in my interval, so we're going to go ahead and like count both of them. All right. The reason it said that you may use a calculator is that's what you would have to do. Quadratic formula. We don't want to do that. Right. Okay. Make sure you guys do. I'm going to do 35. All right. I'm going to show you another thing that you can do. So let's go and clear these now that we're done with that one. Okay. First of all, make sure you're in radians. All right. I'm going to go sine x plus sine 2x. Now, even if it's something you don't like want to take the derivative of, you can actually do this. Math 8, and then you can put alpha trace y1, and then what you have to do is you got to put x equals x, and that will do the derivative everywhere. Okay? So when I graph it, that's my original function. That's my derivative. The red one is my derivative. All right? But remember, mean value theorem says we got to do derivative equals slope. Oh gosh, that's continuous and differential. Okay, this one is also continuous. And 34 is also continuous and differential because it has a vertical asymptote of 1, but that's not in my interval. All right, anyways. Okay, now I need to find the slope. Let's go out here and let's do the same thing. Alpha y equals fraction, alpha trace y1 of pi minus alpha trace y1 of 0 over pi minus 0. Okay, easy enough. It's 0. So I can go ahead and put 0. Now, I'm going to turn off my first one just so it doesn't. And I go to my graph. So it's graphing the derivative right now. And then it's graphing the slope. And I have to see where they're equal on the interval 0 to pi. Okay, now if you want to change your window, well, first of all, I can go like negative 5 to 5 on the y-axis, but I can go 0 to pi. Then I'll only see what's in my interval, and I can change this like 5 to 5. Because that was under window. And then let's go back here. Looks like there's one, maybe 2 places. Okay, so let's go ahead and find the intersect. Go over here. Let's hit 1, 2, 3. So my first point is 1, 7. And let me see if there's another one. Like there's one right there. Get close, hit enter 3 times. And it's still jumping back over there, which I guess means the other thing you guys can do, that we're allowed to use Desmos are that's not also 2 plus 9. Oh, except for I'm actually not sure how to do derivative on here. I don't know if we can like graph the derivative, but we would have to take the derivative a little bit. but we could do that. The derivative would be 2 times and then plus 2. That one off. And then we can actually just see where it hits, and it's at pi over 3 and pi. Okay, and pi was my endpoint. That's why I only got one answer, and it looks like that answer. All right. Oh, excellent. Here things. Number 34, number 24, and number 30. Okay. And please make sure to have this part. All right, by next time. Awesome. Thanks, guys.